So how do we know that value iteration will actually converge to the true state values as we define that? We define that very specific V star value, the state value when we follow the optimal policy from a given state. So in order to prove convergence, to prove that value iteration will actually converge at these values, we first prove that the Bellman operator is a contraction mapping. What does that mean? A contraction mapping means that if you take two value assignments, right, for all of the state space, the largest difference between any two states, between any specific state in these two value assignments, the largest difference when it's discounted must be greater or equal to the largest such difference, but after we perform the Bellman operator over both of these state value vectors. Okay, so this is the definition of a contraction mapping, and I also included here a proof that the Bellman operator is indeed a contraction mapping. I won't go over this proof because it's a bit of a waste of the time, and we'll have to introduce, we will really need to break it down to see that we understand everything, but I included a very, very detailed proof here. I actually wrote out every step in the process, so it should be fairly easy for you to follow it, and you're more than welcome to do that. But I won't do it at the moment. Okay, so once we prove that the Bellman operator is a contraction mapping, now we can actually prove that value iteration converges on the true utility value. That is, at the limit, if we perform value iteration over and over again, we are guaranteed to converge on V star, on the true state values. And the proof follows as follows. First of all, the Bellman operator has a fixed point at V star. That is, if you'll assign the V star values to all of the states, and you'll perform a Bellman operator on those state values, you're guaranteed to remain in a fixed point. The state values will not change. So this is just a proof that, or it's not a proof, but you can easily prove that the Bellman operator will result in a fixed point at V star. And secondly, a contraction mapping has at most one fixed point. And moreover, the Banach fixed point theorem states that every contraction mapping on a non-empty complete metric space M has a unique fixed point, and that for any x in M, the iterated function sequence x, fx, f of fx, f of fx converges to that fixed point. Okay? Question? Yeah.
Professor, so would this mean that the value function, the optimal value function, is unique?
Yes, it does mean that the optimal value function is indeed unique.
Okay. And would that mean that the policy that we obtained from this value function, would that also be unique?
Not necessarily. That's not necessarily the case. I did show you previously that you can infer a deterministic optimal policy from the state values, but it's not necessarily unique. We can actually infer several different policies from a given V star values. Okay? Okay, so let's go back to discuss our grid world example. So just as a reminder, this is as previously, we have an agent that lives in a grid. The wall blocks the agent path. It has a 0.8 probability of actually arriving at the intended next state that it intends to. That is, for instance, if it's in location 1, 3 or 3, 1, depends how you set these coordinates, and it would like to go up, there is a 0.8 probability of actually succeeding in doing so, and then a 0.1 probability of slipping to each one of the sides. We have a small negative reward at each time step, right, representing battery drain, and we have a big reward, either positive or negative, at the end of the game, either -1 or +1, as depicted here on the right. As before, our goal would be to maximize the sum of discounted reward, to find a policy that maximizes the expected sum of reward. Okay, so let's see how would value iteration work in this space. And so, right, some of the parameters in this domain, we set the noise to be 0.2, so there's a 0.1 probability of slipping to each one of the direction. The discount factor is set here to 0.9. And we set the leaving reward to just be 0. Okay, so you only get a reward at the two endpoints. You get a +1 here and a -1 here. -1 here. So let's run value iteration. So at k equal the first iteration, we just initialize the state values as zeros. Next, we go over our entire state space and update the state value based on one step look ahead, so equivalent to a one step look ahead. So this will be specifically as we set the leaving reward to be 0. It will just be represent the rewards, the immediate rewards that we observe at the terminal states, right? +1 and -1. Next, we'll continue to propagate these values downwards. And this represents, at k equal 2, the immediate reward that we can gain from each state when performing two actions, right? A time series of length 2. By the way, Vav, do you have any idea why the value here is still 0? So the -1, the bad value, was not propagated to the state here that I paint with red, right?
Yes.
This one. Why is that?
I mean,
sure. It did. So the positive value did propagate here, but the negative value did not propagate here. How come?
I'm not sure. Why is that?
How come? Why is that? That's a good question, right? So the reason is -1 is actually worse than the 0 that it could have get by going to either up or down. So this was going up was not 0.72 in the previous iteration, right? It was 0. So the agent would have get 0 if it went up or down. It actually got up or down, and it never wanted to go right and get a -1. But you might say, yeah, but there's always a chance that it slipped and went to -1. Well, yes, but probably the action that maximizes the expected reward in the based on these values would probably be, actually you can see it here, it would be go left. If it go left, with probability of 0.8, it would stay in place and get a reward of 0, and with probability of 0.1, it would get 0, probability of 0.1, it will also get 0, but it will never get the -1, and we'd like to avoid doing so. So we are left with a value of 0. Okay, continuing, K3, you can see that the positive value is propagated to the neighboring states. So in 3 steps from these 2 states, we can also get to +1. We continue this process, and the values propagate backwards over time. And the interesting thing to see is that over time, so this is k equals 6, the change in these values becomes smaller and smaller, right? We actually proved that it's a contraction mapping, it happens over time. So we didn't prove, okay, so the contraction mapping didn't prove that all of these values, the difference will diminish over time. The contraction mapping proved that the largest difference in the state space does reduce over time. Okay? Yes, question?
If both the terminal states had negative rewards, would the value still propagate, or would they all stay 0?
No, so if they both were negative, the agent will never, right, they won't propagate the negative value, it will just stay away.
Because you never want to go to the negative.
If it has a chance not to get the negative reward, it will never propagate back. It will say, I'll never take an action towards the negative rewards, right?
That was a silly question.
No, there are no silly questions.
You never go to the negative state. Yeah, makes sense.
No silly questions. Okay. But you can see that the updates diminish over time, the magnitude of the updates, right? And so for instance, between k equals 9 and k equal 10, I guess that the largest delta here was 0.2. 11, this was 0.1, I think only this one changed. And then you can continue, and the changes, there are still changes, but you can continue up to k100, right? From k12 to k100, there's barely any change, right? So This shows you that over time it does converge. It also shows you that value iteration is a bit wasteful, right? I mean, you continue to do the full sweep over the entire state space, but the changes are become insignificant over time. Okay, and so this leads me to discuss some drawbacks of value iteration. It's a good approach, it works, it will converge. It has some unreasonable assumption, like we know the transition probabilities, right? We need those, and we know the reward function. We need those in order to perform the Bellman update. But beyond that, value iteration also has some other issues. Let's discuss those. And we'll also see how we can maybe address some of them.